Hi, in today's video I have a spectral analyzer to review. This is the tinySA Ultra, a portable spectral analyzer with a usable level calibrated range up to 6 GHz, and it can observe signals up to 12 GHz according to the manual. The specs are certainly very impressive, considering this is a tiny device, costs just around $150. In this lab, we definitely have the right equipment to test this spectral analyzer to its limits, so we will have to see how it performs in real world a little bit later. This unit was provided to me by Banggood. As usual, I'll leave a product link in the video description below for those who are interested in getting one. A spectral analyzer measures the magnitude of an input signal for a given frequency range. Often you can see it being used to measure and characterize RF circuitry, such as testing oscillators and determining the levels of harmonics. It can also be used to characterize filters, modulations, and so on and so forth. In the past, most hobbyists, unless they were very serious about RF stuff, probably didn't have a lab-grade spectral analyzer, and this is because, unlike other test equipment, spectral analyzers tend to be very expensive, even for used ones. I happen to have a very good spectral analyzer, the 4 decades old HP 8566B, that you probably have seen me using in a lot of my videos. The 8566B can measure up to 22 GHz, and even by today's standards, it remains a very capable machine. But a fully functional unit is hard to come by these days, and it will probably cost you at least a couple $1,000. And the 8566B is very heavy, with a combined weight of more than 100 pounds. Anyway, obviously we can't expect the same level of performance from this tiny spectral analyzer, no pun intended, but it would still be extremely useful if we can get any kind of meaningful measurements from this $150 device, especially given the claimed capabilities. So with the expectations set, let's power it up and take a closer look. Oh, before I do that, I just want to quickly show you the accessories came with this spectral analyzer. And you can see here is nothing that unusual. You have 2 of these SMA cables, a through connector, and an antenna, and of course you have a USB-C cable here. The tinySA also comes with a 32 gig microSD card pre-installed. The tinySA Ultra has this 4-inch LCD, and unfortunately the LCD is glossy, so that's why I have it propped up like this. Otherwise, due to reflection, you wouldn't be able to see anything on the screen. By default, it's sweeping between 0 and 800 MHz. This is the standard mode. The Ultra mode, which will enable us to look at signals beyond 6 GHz, will need to be enabled explicitly. So let's do that first. So config, more. You can see we have this enable Ultra box that is unchecked. So let's check it. And we need to put in the passcode, which is listed on tinySA's website. So it's 4321 and enter, and it's that simple. So now we have the Ultra mode enabled. Once it's enabled, you can see the default stop frequency now is set at 3 GHz. And the reason the Ultra mode is not enabled by default is because there are some caveats that you need to pay attention to, as the Ultra mode has some limitations. For instance, in Ultra mode, the input low-pass filter is disabled for frequencies above 750 MHz and will cause LO leakage and affect your measurement. Also, the measurement will be slower as multiple passes are needed to remove spurious signals and mirror images algorithmically. So let's first test our sub-800 MHz frequency band, and then we'll move on to the gigahertz frequency bands later on. And before we do any testing, let's follow the calibration procedures and calibrate the lower band first. To calibrate, I'm going to use the stock SMA cable and connect a cal port. Let's finger tight it to the RF port. You don't need to over tighten these connectors, just finger tight will be sufficient. And let's come here, let's go back, level cal. And we are going to calibrate from 100 kHz to 5.34 GHz, and we'll take a look at the other calibration a little bit later on. Calibrate. Alright, it did take a minute. The calibration now is completed. Now let's take a look at the self-test. Alright, looks like self-test has passed. Okay, now I have powered up my HP8642B signal generator, which is humming in the background, and I have it set to outputting a 100 MHz minus 10 dBm signal. So let me enable the output. And now you can see that we have captured that signal on the spectral analyzer here. This peak here is minus 11.1 dBm, which is accurate enough, as I do have a pretty long SMA cable here. And we also have a few harmonics that you can see detected from this 0 to 800 MHz scan. So let me center the frequency on the 100 MHz here. So let's do frequency center 100 MHz. And let's do a frequency span of 1 MHz. So that is our signal, nice and clean. Currently, the resolution bandwidth you can see is automatically set at 10 kHz, which is pretty good. Of course, if we were to increase or decrease the resolution bandwidth, you will see that the scan speed is going to decrease significantly. So here is at 3 kHz resolution bandwidth. And so let's set it back to 10 kHz, as that is going to be good enough here. And you can see that the signal captured here is very clean, and we have a noise floor of well below minus 75 dBm. And I just added some amplitude modulation to that 100 MHz carrier signal. Right now we're using a 100 kHz modulation frequency, and the modulation depth is at 100%. I think what I'm going to do is I'm going to also capture the same spectrum on the HP8566B spectral analyzer and overlay it on the video so I don't have to switch back and forth. And here you're looking at a frequency modulated signal on top of that 100 MHz carrier frequency. The signal that's being modulated is a 50 kHz signal, and the frequency deviation currently is at 100 kHz. Right now we're putting in an 800 MHz frequency, and that is at minus 10 dBm as well. As you can see here, we are able to capture that signal at minus 13 dBm, which is typical as we do have some cable loss here. And the reason I want to show you this 800 MHz signal is because the standard frequency range without enabling the ultra mode is 0 to 800 MHz, and right now we're at that upper end. And if you look carefully, you do see that the noise floor is not flat anymore, and actually towards the upper end we are started rolling off. Now, the reason I'm not sure is actually the noise floor is getting lower, or it is just because we actually are currently calibrated up to just 800 MHz, and after which the measurement probably is not accurate anymore. And here is an amplitude modulated signal. The modulation frequency again is at 100 kHz with a 100% modulation depth, and you can see that we do have some asymmetry here. Let me change the frequency span a little bit here. So let me change it to, instead of 1 MHz, let me change it to 2 MHz. Yeah, as you can see here, we do have some artifacts, and I do suspect that it's actually because we only calibrated up to 800 MHz. So let me actually reduce the frequency, and let's do that again. So let me, instead of 800 MHz, let's do 799 MHz. And this is a 799 MHz signal. As you can see that everything looks great. And again, this is the 799 MHz signal with the amplitude modulation enabled. Currently, the modulation frequency is at 100 kHz with a modulation depth of 100%. And here is the same 799 MHz signal with a frequency modulation added on top. The frequency modulation here is with a deviation of 100 kHz with a modulated frequency of 50 kHz. Again, here, if I change the carrier frequency to 800 MHz, which is what we're sitting at right now, you can see, you do see some artifacts at right above 800 MHz. Now I have just set up a sweep from 95 MHz to 100 MHz, and the sweep time is currently set at 2 seconds. The amplitude remains at -10 dBm. And as you can see, we are having a little bit of trouble keeping up with the sweep signal here. And here the resolution bandwidth is at 100 kHz. Let's see if we can slow it and make it better here. So let's do a 300 kHz. Yeah, it's slightly better as we are able to update faster here. So let's go back to 100 kHz. To capture time-varying signals, such as the sweep signal, the sweep time of the spectrum analyzer will be very important. And for the tinySA, you will see the limitation here. And there's nothing wrong with that. It's actually somewhat difficult to perform fast sweeps, not just for this tinySA, but for many lower-end SAs in the market as well. This is due to the settling time of the filters during the measurements. Now for the HP8566B, it uses a IG or yttrium iron garnet tune filter, which can be tuned very fast electronically, but that is a totally different architecture. One cool feature is that you can also enable the waterfall display, and let me just show you here. So let's go to display, and let's enable waterfall, and by the way, you can press it again. It will actually make the waterfall display even bigger here. So let me just show you here if I press it again. And this is actually a cool feature, especially if you wanted to see the frequency drifts over time. And right now I'm setting this band as our FM broadcast band. You can see that I have an antenna hooked up. So this is between 88 MHz to 108 MHz. You can also listen to the demodulated signals with the tinySA Ultra. I did a full video on the theories behind this many years ago with my HP8566B, and I will provide a link here if you want to dig deeper. But let's try it out with this tinySA Ultra. So let me hook it up with an amplifier here and turn the amplifier on. Let's go back here. And I think it is at level. And listen.
And we want to continue.
And that's our station here. And you can see we can tune it differently here. So let's tune to a different station here. So let's try a different station. Let's try the one up here. This one is a strong station here. By the way, I'm in the basement, so the reception is not that great. Alright, so you got an idea here. Okay, let's get out of the listen mode. Now, compared to the result I had with my 8566B, the sound does seem to be a little bit more distorted, and this largely depends on the filter implementation, of course. This feature actually is quite useful if you are troubleshooting transmitters. Now let's take a look at signals in the gigahertz range. And before we do that, we do need to calibrate the range above 5.34 gigahertz, as if you recall earlier, we did the calibration for the lower band. And now we need to calibrate the 5.34 gigahertz and above. So let's do that. And they ask you to connect a 5.34 signal source between -50 to -10 dBm. For that, I have already hooked up my HP8671A synthesizer. And that synthesizer currently is outputting a 5.34 gigahertz signal. Unfortunately, the signal output is not leveled, so to make sure we are within this power range, I have added a couple pads. So we should be all right. And right now the output is probably at around minus 15 dBm. And it looks like we are done here. And right now you're looking at a 2 GHz signal that is at minus 10 dBm. Of course, we're detecting a little bit lower because of the cable loss. Currently, the frequency span is at 10 MHz. You can see that we do have some lobes here that is not from the signal. So this is some artifacts from the tinySA here. And let me reduce the frequency span to 1 MHz, and we'll do the same testing as we did before and see how it looks here. So here is 1 MHz, and you can see also we have this roll off. This is definitely artifacts introduced by the tinySA. And here again, we just applied a 100 kHz amplitude modulated signal at 100% modulation depth. And you can see that the measurement is pretty reasonable, and we do have a little bit of artifacts towards the right half of the signal here. Again, this is our frequency modulated signal with a frequency modulation of 50 kHz with a deviation of 100 kHz. At this higher frequency, you can see that the scanning is considerably slower, even with this 1 MHz frequency span. And currently the resolution bandwidth is set at 10 kHz. Right now I'm sweeping between 1.8 GHz and 6.2 GHz, and the signal currently is outputted from the 8671A. And is at 2 GHz. You can see here we have a 2 GHz main peak detected here, and we also have a few harmonics. Of course, with such a large frequency range, the scan time had reduced significantly. Currently we're at about 8 seconds for the entire sweep. And the resolution bandwidth also is very high, currently at 850 kHz, but that's not a problem. What we want to see is essentially whether or not we can detect any of the signals in this higher frequency band. One thing I want to point out is as the frequency increases, the noise floor also increases as well. At the upper end here, the noise floor reaches about minus 40 dBm. This is actually very typical as we're using harmonics mixing towards the upper frequency band, and that reduces your signal to noise ratio. We see the same behavior on the HP8566B spectrum analyzer as well. Anyway, let me increase the frequency and see what we get on the spectrum analyzer. And don't pay too much attention to the amplitude, as the output from the 8671A is not level. But let's increase it to 3 GHz here. Of course, we have to wait till the scan completes. No problem. And let me increase the output to 4 GHz. So there's some transient while I was switching the frequency synthesizer. So let's wait again. Yep, now we're at 4 GHz. No issues. And we can see that we are maintaining the amplitude. So that's actually a good sign here. So now let me increase it to 5 GHz. No problem. Let's increase it to 6 GHz. And no issues whatsoever. So to test even higher frequency, now I switch to my WaveTech 907. That signal generator can generate all the way up to 11 GHz. So now I'm setting the output at 7 GHz at 1 dBm. You can see what we have on the spectrum analyzer is currently at 7 GHz, measuring minus 5.5 dBm. The spectrum analyzer currently is sweeping between 6 GHz and 12 GHz, as you can see here, and you can also see the peak we detected at 7 GHz. So let me change the frequency to 8 GHz. And you see that we are able to detect that although the magnitude had dropped significantly from -5 dBm all the way down to -17.5 dBm now. Now, we did read in the manual here, for these higher frequencies, it is expected that the magnitude rolls off significantly due to the front end in this spectral analyzer, but nevertheless, it's still very useful that you can still see the signal on the spectral analyzer. So let's increase it to 9 GHz. And as you can see at 9 GHz, we dropped even further. Now it's at -27.5 dBm, but we can still detect the signal here. So let me change it to 10 GHz. And at 10 GHz, you can see we are now down to -38.5 dBm, but we can still observe the signal. So let me change it to 11 GHz. At 11 GHz, you can see we are barely above the noise floor here at -57.5 dBm, although the input signal is at 1 dBm. And that is actually consistent with what we read in the manual. Nevertheless, we are able to still discern the signal here, which is really impressive for the tinySA. Of course, the tinySA can also be used as a RF synthesizer, and it's actually quite capable. So let's take a quick look here. So to get to the RF generator, all you do is select the signal generator here. And currently we have the output on. You can see that we're generating a 100 MHz signal. It appears that the maximum output level is at -20 dBm. So if you look at the spectral analyzer, let's do a quick peek search here. You will see we're right at about 100 MHz. The measure one currently is at 99.8. It's a little bit off, but that is actually fine because we have a really large span here. And the reason I kept the span this wide is because I want to show you the harmonics. This is a sinusoidal output currently. You can see the harmonics is way down there, right above the noise floor. So the signal quality is very good. And right now I just zoomed in onto the signal. You can see here we have a frequency span of 1 MHz, and the resolution bandwidth is set at 3 kHz. You can see the tone here is very clean. And according to the manual, you can generate a sinusoidal leveled output all the way up to 820 MHz, and beyond that, the waveform becomes unfiltered square wave, which means it will have higher harmonic content, but it will still be usable. So let's take a look at that. Currently, we're outputting an 820 MHz sinusoidal, as you can see here. Now, the output level did drop to about -23.4 dBm, and that's to be expected. As you can see on the spectral analyzer here, we are able to capture that signal here. And the reason I left it to scan all the way up to 2 GHz is because I want to show you the harmonics here. So now this is our second harmonics down right above the noise floor. So let me change the synthesizer frequency to 850 MHz. And you can see the main signal here remains at about, let's just do the peak search here, remains about -23.5 dBm. But now we have a significantly higher harmonic content. That's because we're currently outputting a square wave instead of a sinusoidal. The highest frequency the tinySA can output is 5.4 GHz. As you can see here, we're at 5.4 GHz, but right now the output level is significantly attenuated. It says on here it's almost -30 dBm down, and we're measuring almost 45 dBm, and that's probably because of the cable loss and everything else. The built-in synthesizer can also do modulation as well. Here you can see we have a 500 MHz signal and is AM modulated. The modulation frequency is 10 kHz at a modulation depth of 100%. Then here's our same 500 MHz signal, except this time we have the FM modulation on top. The FM currently is set at 10 kHz frequency deviation. Now let's take a quick peek inside. And here we have it open up. You can see that the tinySA Ultra is powered by this 3 amp-hour LiPo battery. Alright, as you can see here, the board layout is very neat. All the shielding cans are just clipped on, and I have removed them so we can see the circuitry underneath. And let's start from this corner here. The overall architecture of the tinySA is essentially a heterodyne receiver. It uses a mixture to mix the input signal and generate an IF to be further processed and analyzed. So besides some ICs for the RF sections, I'm not expecting to see much, as most of the processing is done with a microprocessor after the signal is down converted. So this section is what is under the first shielding can, that is for the calibration output. And the chip here is an SI4468. It's a radio transceiver chip with a very high sensitivity down to -133 dBm. And this larger component down here, that's the mixer, that's a ADE-25 MH that can mix signals up to 2.5 gigahertz. By the look of it, we also have a couple of SAW filters on the side here. So let me move up here. And this section is the SA input section. In this input section, we have a couple of these very small chips. This one, U22, that's our input switch. And the U14 up here, that's an LNA, or low noise amplifier. The QFN chip here, marked as 4312, that's our step attenuator. And let's move up here. Under this middle shielding can, that is our synthesizer, that's an ADF4350A. And that synthesizer can output frequency up to 4.4 gigahertz. Up here, right next to the power switch, this chip is a CS5181E, that is a lithium-ion battery charging chip. And let's move to this side. And here in the middle, you can see the microprocessor used in this tinySA. It is an STM32F302. And this processor actually does a lot of the things. It not only drives the user interface, but also it implements a lot of the algorithms, including digital filtering for the tinySA. And on the side, we have some programming ports. And next to the battery connector, we also have this boot and VDD connector here. You will need to connect them together if you manage to brick your device during an upgrade, and then you can reflash the memory again. And that's pretty much everything that is on this board. Now we do have a couple of unpopulated footprints by the look of it. One is up here, and one is down here. So not entirely sure what those are intended for. And by the way, you can see that we have this very interestingly shaped ground plane here. Not entirely sure if it has any purpose, but nevertheless, it does look very cool. Anyway, that's pretty much what I want to cover in this video. Hopefully you get an idea of what this tinySA Ultra is capable of. To be honest, I was actually quite impressed with the capabilities of this tinySA, especially considering the price point. For just $150, you have a spectral analyzer that can test signals up to 12 gigahertz, and it also comes with a built-in feature-rich RF synthesizer that can operate beyond 5 gigahertz. I could only have dreamed an instrument like this just a few years ago. This video is really just an overview of this tinySA Ultra, and there are a lot of things you can do with it that I haven't even touched upon yet. If there's anything specific you wanted to see or wanted me to go in a little bit more depth, please leave me a comment below, and I will be sure to make a few more dedicated videos on the topics of interest later on. Anyway, I hope you enjoyed this video and learned something new. If you liked the video, please be sure to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. I will catch up with you next time.